Today, we're tackling Leetcode problem 2033, minimum operations to make a Uni-Value Grid. The problem asks us to find the minimum number of operations needed to make all elements in a given 2D integer grid equal. The only allowed operation is to add or subtract a given integer x from any element in the grid. If it's impossible to make all elements equal, we should return -1. Let's look at the examples. In the first example, the grid is 2, 4, 6, 8 and x is 2. We can make every element equal to 4. To change 2 to 4, we add x once. To change 6 to 4, we subtract x once. To change 8 to 4, we subtract x twice. The total operations are 1 plus 1 plus 2, which equals 4. In the second example, the grid is 1, 5, 2, 3, and x is 1. Can we make all elements equal? Let's see. Maybe make them all 3. 1 to 3 needs 2 adds. 5 to 3 needs 2 subtracts. 2 to 3 needs 1 add. The total operations would be 2 plus 2 plus 1 equals 5. If we picked 2, it would be 1 plus 3 plus 0 plus 1 equals 5. It seems 5 is the minimum here. The third example shows grid 1, 2, 3, 4 and x is 2. Can we make 1 and 2 equal by adding/subtracting 2? No, because the difference is 1, which is not a multiple of 2. Similarly for other pairs. Since we can only change elements by multiples of x, if two elements have different remainders when divided by x, we can never make them equal. In this case, it's impossible, so we return -1. Let's think about the condition for impossibility first. We can only change an element by adding or subtracting multiples of x. Imagine we want to make all elements equal to some final target value, let's call it t. For any element a in the grid, we must be able to reach t from a, using only steps of size x. This means the difference t, a must be a multiple of x. Now, consider any two elements, a and b from the original grid. If they are both supposed to become t, then t, a must be a multiple of x, and t, b must also be a multiple of x. If ta equals k1x and t, b equals k2x, for some integers, k1 and k2, then subtracting these equations gives tb minus ta equals k2x, k1x, which simplifies to a, b equals k2-k1x. This tells us a crucial fact: the difference between any two elements in the grid must be divisible by x. If this condition isn't met, it's impossible to make them equal using only operations of adding or subtracting x. An equivalent way to state this is that all elements in the grid must have the same remainder when divided by x. So, our first step should be to check this condition. We can pick the first element, calculate its remainder when divided by x, and then iterate through all other elements comparing their remainders. If we find any element with a different remainder, we immediately know it's impossible, and we can return -1. Okay, so if all elements have the same remainder modulo x, we know it's possible to make them equal. But what value should we make them equal to? Let's call this target value t. For each element a in the grid, the number of operations needed to change it to t is the absolute difference abs, a t divided by x. Why? Because we know t and a have the same remainder modulo x, their difference ta, or at, must be a multiple of x. So abs, at divided by x, gives the exact number of additions or subtractions needed. Our goal is to minimize the total number of operations. This means we want to minimize the sum of at divided by x for all elements a in the grid. Since x is a positive constant divisor, minimizing sum abs at divided by x is the same as minimizing sum abs at. Now the problem boils down to, given a set of numbers, all the elements in the grid, find a value t that minimizes the sum of the absolute differences between t and each number in the set. This is a well-known statistical property. The value that minimizes the sum of absolute deviations is the median of the set. So our strategy is clear. First, collect all the numbers from the grid into a single list. Second, sort this list. Third, find the median of the sorted list. This median value will be our optimal target value t. Finally, calculate the total operations by summing abs, a median, divided by x, for every element a in the original grid. Let's formalize the algorithm based on finding the median. First, we need to get all the grid elements into a single, flat list. Let's call this list nums. We can do this by iterating through each row and each column of the grid and appending the element to nums. Second, we perform the crucial remainder check. Take the first element of nums, 0, and calculate its remainder when divided by x. Let's store this in a variable rem. Then, loop through all other elements in nums. If we find any element num such that num modulo x is not equal to rem, we immediately return -1, because it's impossible. Third, if the remainder check passes, we sort the list nums in non-decreasing order. Fourth, we find the median element. Since the list is sorted, the median is simply the element at the middle index. If the list has n elements, the middle index is n floor divided by 2. Let's call this value median. Fifth, we calculate the total number of operations. Initialize a variable total_ops to 0. Iterate through each number num in the unsorted or sorted doesn't matter at this point, list nums. For each num, calculate the absolute difference abs, num median, divide it by x using integer division, and add the result to total_ops. Finally, return the calculated total_ops. This is the minimum number of operations required. Here's the Python code implementing the sorting approach we just discussed. First, we get the dimensions m and n of the grid. We create an empty list nums. We then use nested loops to iterate through the grid and append each element grid to the nums list. Next, we perform the remainder check. We calculate the remainder of the first element nums, 0 modulo x, and store it. Then, we loop through nums. Inside the loop, if any num modulo x is not equal to the stored remainder, we immediately return -1. If the code execution proceeds past this check, it means all elements have the same remainder. We then sort the nums list using nums.sort. After sorting, we find the median. The median is the element at index len nums floor division by 2. We store this in the median variable. Finally, we calculate the total operations. We initialize total_ops to 0. We iterate through the nums list again. For each num, we compute the absolute difference, abs, num median, perform integer division by x using vdival, and add the result to total_ops. After the loop finishes, total_ops holds the minimum number of operations, so we return it. Let's analyze the time and space complexity of this sorting-based approach. For time complexity, first, flattening the grid into the nums list involves visiting each of the m times n elements once. This takes om multiplied by n time. The remainder check also iterates through the m times n elements once, taking om multiplied by n time. Sorting the nums list, which contains m times n elements, is the most time-consuming part. Standard comparison sorts take O n log n time, where n is the number of elements. Here, n is m times n, so sorting takes om multiplied by n multiplied by log m multiplied by n time. Finding the median after sorting is just accessing an element by index, which takes O1 time. Calculating the final sum of operations involves iterating through the m times n elements again, taking om multiplied by n time. The dominant factor is the sorting step. Therefore, the overall time complexity is O m multiplied by n multiplied by log m multiplied by n. For space complexity, we create the nums list to store all m times n elements from the grid. This requires om multiplied by n space. The space used by the sorting algorithm itself can vary. In Python, timsort is used, which might use up to om multiplied by n, auxiliary space in some cases, although it often performs better. If we consider the space needed for the nums list itself, the space complexity is at least om multiplied by n, so the overall space complexity is om multiplied by n, due to storing the flattened list. And that's how you can solve the minimum operations to make a Uni-Value Grid problem using the median. The key insights are the remainder check for possibility and using the median as the optimal target value. If you found this explanation helpful, please give it a like, subscribe for more Leetcode explanations, and leave a comment if you have any questions or suggestions for future videos. What other problems would you like to see covered? You can also support the channel and help me continue making videos by donating at buymeaboba.com. The link is in the description below. Thanks for watching.